Good last few minutes of morning, everyone, and a happy Friday to us all. My name is Josh. I'm tuning in from my house as part of the Morrison Planetarium's Facebook page, streaming out to both our Facebook and SETI Live to bring you another Cosmic Conversations. This Friday, we will be speaking to Dr. Katherine Bywaters, who's joined me here on screen. Hi, Katherine.
Hello.
So, Katherine, you work with the SETI Institute. Can you tell us a little bit about SETI and what that acronym means?
Sure. So SETI is the Search for Extraterrestrial Intelligence. I personally work on life detection instrumentation and where and how you would go about looking for life in our solar system.
That's awesome.
SETI does, my focus is just the solar system, but SETI, deep space, they're looking for life all over.
Well, the solar system, our solar system, I should say, seems like a pretty interesting spot these days. There's been a lot of really cool discoveries, and we wanted to give a little bit of context to some of those things that are coming down the pipeline, as well as what this search for life might mean. So we're going to do this via a planetarium program we call Uniview, and we can bring that up right now with our very own place in the solar system where we know life exists, our very own planet Earth. So what can we learn from this one data point?
Right. So the hard thing about understanding what sort of life could be out there and what that might look like and where to look for it is that we only have a data set of one. We have a sample size of one, and that's life here on Earth. So we use what we call analog environments, and those are environments that are some of the harshest, most extreme environments here on Earth, and they represent conditions that we might see on other planetary surfaces. So through studying those areas, we can learn more about where to look.
Now, when we say an alien, are we thinking of somebody like a science fiction movie coming down and finding us? What would an alien be in your context?
The really super intelligent alien with the great technology would be wonderful. That's the dream find, right? But when I think about finding life, particularly in our solar system, it's, microscopic life that you can't necessarily see. So that's the unicellular organisms, bacteria, viruses, something small that you wouldn't necessarily see with the naked eye.
Now, if we found a bacteria, how do we know that that bacteria didn't fly off of Earth and land someplace else?
That is a very good question and very highly debated. You have contamination issues, you have panspermia, which is the idea of interplanetary transport. We know there's been exchange of material between Mars and Earth. We know that there are organisms that can survive these, really harsh environments of space and conditions of space. So how do we know if it doesn't just, originate from Earth? And that's sort of the holy grail of astrobiology, is finding the second genesis, is finding something that doesn't fall on our tree of life. So people in the community might be aware of what the tree of life looks like. This is sort of a very broad representation. You just have, everything stems from the last Luca, the last universal common ancestor. And as we've evolved, we have all of these different branches on that tree of life. So what we really want to find is something outside. We want to find a second tree. So something that doesn't map, even if it shares the same genetic material as us. Yeah, not that one.
Not that one. Those are rubber.
But yeah, so something outside of our tree.
Okay, so when we're looking in our solar system, we tend to keep our view, I don't want to say close to home because it's really not, but not too far abroad in the solar system. We want to stay a set distance from our sun. Is that right?
Right. So we've come up with a term called the habitable zone. And that is the distance from the sun where you would have liquid water processes capable on the surface of a planetary body. And Earth just happens to fall right in the middle of that habitable zone. You have Venus closer to the sun, which is on the edge of the habitable zone, and then Mars, which is farther away from the sun on the other end of the habitable zone. And we'll get back to Venus. I know there's been a lot of intrigue and excitement over Venus, and we'll get back to Venus. But for now, let's focus on Mars and then the outer solar system and what interesting, because there's some really cool and interesting things out there, and then we can get back to Venus.
Okay, so heading out to our fourth planet from the sun, Mars, this is kind of the express trip. Any kind of spacecraft, we'd expect months of travel to get to Mars, but thanks to Planetarium software, just a few seconds. You can see that distinctive reddish color and that rocky surface. So if we're looking for life on Mars, where should we be looking?
Where do you think we should look? Just to kind of you've been doing this for a while. Where would you think that would be a good place?
I'm going to turn this out to our audience. If any of you have a favorite spot on Mars where you really think life should be hanging out, I'm going to start to speculate wildly. It's never stopped me in my career as a planetarium presenter. I would say places where we know stuff like water, so maybe the poles could be a hospitable environment. I've heard interesting things about water on the surface of Mars in the form of briny flows that happen periodically. And we had Brian Day tell us about some sheltered areas below the surface where we might have a little bit of sunlight reaching an area, but not too much. Looks like Sharada is suggesting the equator. Life flourishes at Earth's equator, so I can see that being a pretty good spot, especially for receiving solar energy.
Right.
Any other ideas floating around? Well, Catherine, are we close? How far off are we?
Those are all very good places. We know that Mars was warmer and wetter in the past. There was definitely liquid water on the surface. And there's potentially oceans, but we have sedimentary deposits, all of these signs that there was liquid water on the surface. So if there was life on Mars during this period of time when it was warmer and wetter, we might be able to find, the last outpost for life, such as the places like these briny salt deposits or frozen, you have ice deposits, as well as in lava tubes. So that is one of the places that has been speculated might be a good place to look for life. We know that caves here on Earth are little ecosystems all of their own, right? They're very self-contained, and they can protect from, harsh desiccating, so being dried out or being bombarded by UV. They're very temperature stable, or can be. So maybe these might be nice places on Mars to look for life and go exploring for signs of life. And here, these are great pictures that you pulled up. So these are actually, you're looking into lava tubes. So they're pit formations where you've had the top structure collapse, and you actually have access to these lava tubes. And this has been a place where people have proposed landing and sending robotic exploration to look into those tubes.
So if I wanted to give some context to these pictures, we're looking straight down onto the surface of Mars, and
Yes.
these very, very dark spots where it looks like someone dropped a black hole on the surface is where sunlight isn't striking. So the sunlight is still falling through that, but must be off in the distance underneath the surface somewhere. We're seeing that empty space, the very top of that tube. If I wanted to see an analog for a structure like this on Earth, where could I go?
There's quite a few different analogs. There's a team actually of SETI researchers that are doing cave explorations near Lassen in California. There's Hawaii has. I'm not sure about the actual tube structures in Hawaii, but there's a lot of volcanic exploration and investigations being done at Hawaii. They have an analog research sort of center set up there as, where they go and run through protocols of how you might do exploration on Mars. So there's these great locations in the Arctic on Devon Island, there is the Houghton Impact Crater. Now, that doesn't have any tubes, but it is a pristine, preserved impact crater where we can observe some of the features that we see on Mars, like the gullies running down the crater sides. And so if we want to look at different gully formations and look at what we call recurring slope lineae, those are those sort of streams that you see that seem to wet out and then dry with the seasons. And that's been considered one of the briny, might be a briny causing a briny solution causing those. And by briny, I just mean a really high salt concentration. We have these analogs all over Earth that we can investigate.
Sounds like we had a couple questions pop up. Are there active hydrothermal vents on Mars, or are they all extinct now? Maybe about the geological history of Mars.
Right. So volcanically, Mars is not, we're not seeing that hydrothermal geological activity happening currently on Mars right now. So one of the things about Mars is that it was very geologically active in the past. It's got, the highest mountain there. And you can still see evidence. Are we zooming in to it?
I'm trying to get us into Olympus Mons. Hold on one sec. There we go.
We know it was really geologically active in the past, but Mars is much smaller than us. So it has cooled considerably, and it's not necessarily a dead planet, but it's much, much less active, simply because it's smaller, it's cooled, and you're not seeing that geological activity that we see here on Earth.
So if we had any underwater volcanic activity, something like a hydrothermal vent, it probably would have shut off long ago.
Yes.
We do have some hydrothermal vents elsewhere, but it looks like Faraz has a question about the likelihood of silicon or something with similar chemistry replacing carbon for a life form out there in the universe.
It is possible. Silicon has the similar bonding configuration that carbon has, and that's why it's kind of been proposed as an alternative possibility for life, for the carbon-based life. The problem with that is that the use of carbon is much more energetically favorable. The bonds are just it's more favorable. So if you're trying to construct life and you have a lot of carbon around, and we know that carbon's very abundant, it's most likely carbon's going to win out. So it's not that it's not feasible, it's just that if you look at the energetic standpoint, from an energetic standpoint, carbon is by far better.
So given equally plausible outcomes, we're favoring carbon, but in the absence of carbon, maybe silicon.
Sure.
So we spent a little bit of time in what most folks would call the inner solar system, checking out Mars. I wanted to take us a little farther out from the sun. Things are going to get colder and more challenging out here, but we're still looking for water. So that seems a little counterintuitive.
Right. So NASA has had the Follow the Water slogan for quite some time now. And, we know that life here on Earth needs water to survive. So going off of that data set of one, we're going to be looking for places with water. And we talked about the habitable zone where you have liquid water on the surface. But even in our solar system, outside that habitable zone, we still find liquid water. And we find liquid water on some of the moons of Saturn and Jupiter.
We're out to Europa right now, but it's a little tough to tell the difference between a Europa and Enceladus from a sufficient distance away.
So this is Europa. It's an icy moon. And what that means is it has this thick layer of ice on the outside. There we have Jupiter in the background. Beautiful. And then underneath this thick layer of ice, you have a liquid ocean and then a rocky core. The reason why water is able to exist way outside into this kind of frozen outer solar system region is because of the tidal forces. The tidal forces between the other moons and between Jupiter create sort of this push-pull dynamic. And that's what enables this liquid, the liquid water to exist on the moons like Jupiter and Enceladus. This is, since this discovery, it's been one of the key targets for life detection missions. Can we go back to the surface where you can see the red lines or those?
Absolutely. We even have a close-up if you want to check it out.
Oh, great. So what we can tell is most of the ice is just pure ice, but you have these sort of red lines that run through this ice sheet. And it's thought that this is sort of mineral concentration. So as you get that push and pull from gravitational forces, it creates cracks in the ice where you have water coming up from the ocean below. And you get this, a heavier mineral precipitation there as the water leaves the surface. So if we were going to go for, say, a lander mission there, landing in one of these cracks where you would have more recent activity and more recent geological material being deposited, that's one of the lander options that have been proposed. So to go there and look at that fairly recent ice deposits for any signs of life in the ocean below.
That's pretty amazing. So with this cracking material, it's likely rocky stuff being brought from far underneath up to the surface and deposited?
Well, I wouldn't say rocky. I would say more salts and minerals that are in solution. So they're dissolved in the water. And then as the water is sort of coming off, because as soon as it gets exposed to space, you're going to have sublimation, evaporation. So you're going to leave behind the minerals and salts that were dissolved in that water.
That's awesome. We had a question pop up. I'm sorry, I missed it. From Corey, do you have a favorite moon in the solar system, whether related to your work or not?
I really like Titan, just because it's one of those strange chemistry places. I love the water moons, the ocean moons. I absolutely love them. I think they're a great place. But we kind of know what chemistry to expect, if we go to Enceladus, we know that from sampling, Enceladus has this plume that's shooting liquid water out into space. And so...
Why don't we go see Enceladus while we're talking about it?
Let's go see Enceladus. And I will get to the answer of why I love Titan so much. So here's Enceladus. It's a moon of Saturn. And we know that so it's the same sort of concept as Europa, except for in these cracks, there are very predictable plumes that come out. So this is kind of like a fire hose jettisoning water out into space from that liquid ocean.
You can see some right there.
Perfect. So we've actually, the Cassini probe flew through this plume, right, and sampled it, and we could tell from the chemistry, we think that there's actually hydrothermal activity happening in the ocean of Enceladus. So you have that ice layer, a liquid water, and then if you look here at the very bottom, you can see those sort of red jets. So this is going to be a hydrothermal activity where water is able to be heated. We know that hydrothermal vents here on Earth and our oceans are actually teeming with life. So this is a great source of chemical energy. Because if you look at how thick that ice is, sunlight's not going to get through there. And we know sunlight drives life on this planet, but it wouldn't here. So your form of energy would be chemical, most likely coming from those hydrothermal vents. And so I love these. I think they're great locations. Definitely, I think we need to go there. But this is all chemistry and sorts of environments that we know. We have environments like this on Earth, the deep sea vents, maybe not quite such thick ice, but we know liquid water environments. Titan, on the other hand, is truly an alien world. I mean, it's something that we don't have anything currently on Earth that is a model for this. We have to kind of make experiments in lab to represent what we're seeing here. And I think going to Titan is going to really expand our knowledge base and allow us to learn so much more than we already do.
Now, looking at Titan, we can't see much from outside. I kind of just see an orange glowy ball. Can you give us some context for why that's the case on this moon? No cracks, no fissures?
Right. So this actually has an atmosphere. It has a very thick chemical atmosphere that we can't see. If you zoom in, it's really, remember, it's far out there. It's really far out there. So it's really cold. And what you're seeing is not water. It's not like a cloud water atmosphere. What it is it's this organics. You're actually seeing organics. And if you can see onto the surface of Titan, there are lakes of ethane and methane. So you have these liquid substances that aren't water forming these lake-like features. There you go. And then you can see this sort of cloud haze. And this is organics being, volatile organics coming up. And then the limited amount of UV that does reach the surface of Titan is interacting with these organics. You're getting some strange chemical reactions that are happening. You get them raining back down to the surface. You have dunes of, odd chemical material, organics that have fallen out. So this is why it's just so exciting of the things that we could possibly learn. And NASA, it's actually the target of one of NASA's upcoming missions. So Dragonfly is going to go there. And Dragonfly is just really cool. It's an opticopter. So it's going to come descend onto the surface of Titan. And then it's got these 8 little propellers where it can actually hop around on Titan, taking measurements, looking for, just interesting things that, maybe signs of life, but really analyzing that organic material. And when I say organic material, that doesn't mean that it comes from life. It's just material that life uses. It's carbon, it's carbon-based molecules.
Very cool. I had somebody give me the analogy of, what was it? Legos versus like Playmobil. It's
Yes.
of the same system. We can use it. The other stuff we can't use so readily. So
I like that.
Let's see. How do we know what's inside these worlds? We have pretty good guesses about what's in our crust, even though we haven't gotten down there. How do we even begin to speculate about what's inside another planet or moon?
So, there are people that are just so talented at coming up with very clever ways of finding out. Like if you look at Enceladus or Europa, we know it's the rocky core, the ocean, the ice, and that is from looking at gravitational data and seeing how the changes in the ice happen, and so like shape changes, and the Cassini probe that went through and measured that plume material, measured sort of that hazy atmosphere of Titan. There's a very
see a little tiny Cassini hanging out in this photo.
Perfect. Yeah, so it's teensy tiny Cassini there. So that's it's a lot of I think you have to go back all the way to the time of Galileo, when Galileo first observed the 4 moons of Jupiter. And so you've got Jupiter has tons of moons, but these are the 4 Galilean moons because those are the ones that he could see. And he was able to calculate their rotational periods and just absolutely so much data from merely observation and measurements in the night sky. And this, allows us to understand their mass. And if we know their size and their mass, we can figure out their density. And from knowing density, we can kind of get an idea of what material would make them up, because the composition is going to be elements that we know, right? So by knowing the density, we can kind of figure out the composition. By knowing gravitational forces that Jupiter might have on its moon, or one moon on another moon, we can understand, also their size. And just so it's an investigatory process where you're piecing together information using indirect measurements and direct measurements sometimes.
We've talked a little bit about this with some of our school groups that come through. When we get the knowledge of the density, you can start telling apart your beach ball planets from your bowling ball planets, or your
Yes.
basketballs from your bowling balls. They're about the same size, but even without drilling inside, one of them has different insides than the other.
Right. And that's, it's also, if you think of sort of the seismic activity and watching waves propagate through Earth, that's how we're able to tell what the layers and composition of Earth are. We can do the same sorts of experiments on Mars or the moon and really look at interiors without drilling. You don't have to have huge drills and take massive core samples to understand what's inside.
Well, we had a couple questions pop up about climate change, around haze, and I think this is a wonderful segue to go visit something that's been in the headlines recently, which is Venus. So I'm going to take us in there. There was an announcement, I think Monday this week, that has taken the internet and people's imaginations by storm about the discovery of an interesting chemical compound. I believe phosphine, but I want someone with better chemistry experience than I to confirm that.
Right. So it's
Can you tell us
phosphine.
anything about it?
Well, it is one of those chemicals that here on Earth is either made by humans or biology. It takes a lot of energy to make it. So just by it's not going to just happen. It does form in sort of your gas giants because you have a lot of temperature and you have a lot of pressure, and that can create this compound. But on the clouds of Venus, you're not expecting to see that. And phosphine's actually been one of the things that have been proposed as a biosignature, right? So we've been talking about our solar system, but what if you wanted to go look for life on an exoplanet? What would you look for? And phosphine's been sort of a candidate molecule that you would go look for if you were looking for life, because it's a byproduct of life. And when I say it's a byproduct of life, it's actually a byproduct of life that doesn't use oxygen. So it's toxic to us. If you use oxygen, it's going to kill you. But you have places sort of in these marshy swamplands that your organisms don't have access to oxygen, and they're going to be producing some of them are going to be producing this chemical. So even though it's harmful to life, it's also produced by life. There's so many different flavors of life here on Earth. It's crazy. So that's where some of the confusion comes from. But so this has been a candidate biosignature. So we weren't expecting to find it on Venus. When we find it in the clouds of Venus, it now makes us rethink our position on what sort of biomolecules we might be looking for.
Now, we can see the clouds of Venus, obviously. They do not look like the clouds of Earth. What's the big atmospheric differences between Earth and Venus?
So Venus is on the surface. So they're both terrestrial planets. Venus is often considered our twin because it's roughly the same size as Earth. It's right there on the outside of the habitable zone. We believe that there was liquid water on the surface of Venus in the past, and that the atmosphere built up. You had this runaway greenhouse gas effect, and so you have all of this chemical atmosphere that's trapping heat on the surface, and so Venus has one of the hottest surfaces. It's about 900 degrees Fahrenheit. So very, very inhospitable, most likely never going to find life on the surface of Venus. But in the cloud layer, it's still pretty mean. There's a lot of sulfuric acid, things like that, but there is some water vapor. And in the clouds, it's very similar to our pressures and temperatures that we see here on Earth. Someone's described it as, t-shirt weather in the clouds of Venus. So it is a place where you could have, it is a habitable environment from just a strictly, it has the nutrients, it's got some water, it has nice temperatures and pressures, so it could support life as we know it. There's the possibility.
So I had a question pop up a second ago that I feel like might be relevant. Um, do you think that finding and having habitats in outer space will solve our problems and challenges here on Earth? Like, could we all blast off and live on Venus? Is
You
that
know,
a viable opportunity?
but I think it's very hard to run away from your problems. I think we would take a lot with us. And right now, our technology, I don't think right now our technology is at the point where we could actually support massive civilizations elsewhere. Sure, we could set up some colonies on Mars, maybe sort of the cloud of Venus sort of bubble world that's been depicted in a lot of sci-fi. But to support the amount of water and nutrients and agriculture that we need to support a population, I don't think we're there yet right now. I think the planet with the most resources, the most opportunity, the best chance of survival is Earth, and we need to just invest in our home planet. I mean, don't get me wrong, I think we should absolutely set up colonies on Mars and Venus. I think it would be great. We should do it, but I don't think we should be looking at that as a save the human race at this point.
Very well said. So for folks who are interested in these topics, we've had a couple speakers from the Astronomers for Planet Earth. If you folks want to check it out, they've got a lot of great reasons why, if we want to try and make an Earth-like planet, Earth-like in our solar system, there's one leading option, and it's Earth, because most of the work is already done. So if you are interested, I recommend checking out astronomersforplanet.earth. Great website, great organization, and they can help answer those questions. So a question from earlier, would fossilized evidence of life be visible on Mars underwater flow areas, given the fact that there's erosion or stuff would be buried on top of them? What are we looking for? How would we find fossilized evidence of life on Mars?
So fossilized evidence is very intriguing, and you want to get excited about it. The thing that you have to realize, though, when thinking about Mars is the period of time that Mars was warm and wet and habitable. We know that that sort of span of evolutionary time here on Earth, we still only had, single-celled organisms. So even if you had like microbial mats, you might see maybe some stromatolite fossils, something like that. But they're most likely not, unfortunately, not going to be like dinosaur fossils on the surface or anywhere on Mars. You're going to be looking for signs of past microscopic life, which is much harder to sort of get that smoking gun and be like, aha, I found a fossil of a microbe, right? We do have some early fossils of stacks of microbes, but the microbial mats that you see if you've been to a hot spring, but looking for fossils is going to be difficult,
especially from orbit. So
yes.
Another good reason to get down to the surface.
Exactly.
Okay, I think that catches us up on questions. Is there anything else you'd like to share with our audience while we wait for those last few questions?
Since we're here on Mars, I just want to point out some of the cool things that have happened there in the past and is happening there now. There is NASA's real first flagship life detection mission, right? The mission that NASA actually went to Mars looking for life was the Viking missions, the Viking landers. And they scooped up material, kind of put it in a chicken soup broth, and looked for things to grow. We now know that that's probably not the best way to go about looking for life. First, if you have an organism that's used to living in a really dry environment and you throw it in a bunch of water, it's probably going to kill it. But
stands to reason.
But they really did the best they could with the tools that they had, and it's just so inspirational that that leap of faith was made. It did, however, when it didn't work out, kind of put the brakes on sort of those missions that were that ambitious, because you want to have data. You're spending billions of dollars. You want to learn a lot of things, right? But that brings us to curiosity. So there's been a lot of landers and rovers that have happened. Mars is by far the most investigated planetary surface in our solar system, other than Earth. And so now we have Curiosity on rover. And through the compilation of all the things that we've learned, it's pretty exciting. It's in Gale Crater, looking at these sedimentary deposits. So sedimentary deposits are where you had water, you had liquid water at one point in time depositing small grains. And it's actually able to kind of just scrape off under the surface, dig into the surface, and look for signs of past life or biomarkers or ingredients that life could use. So Curiosity has found organics, right? So there are organic materials there on the surface of Mars, and it's, we've learned so much about the chemical makeup, and there's no reason why life couldn't have existed if it had all the necessary ingredients to have arisen on Mars in the past. Whether or not it did, we still don't know, but at least we know that it was a possibility.
Okay, so let's see. What are some of the candidates for life on planets outside the solar system? I know you said you specifically focus on solar system, but let's take a big step back.
Well, there's so many exoplanets out there. It's actually relatively new thing to understand that there are so many exoplanets. A while ago, we didn't know. We knew that there were all those stars out there. You can see them just by looking up in the night sky. But whether or not there were planets around these stars, we really didn't know until fairly recently. And it's just been this deluge of information. And all of these, if I'm right, the blue ones are exoplanets here.
Mm-hmm.
Okay, so if you look out there, all of those are, exoplanets, and those are just the ones that we've been able to observe. I'm sure there's far more. So I think that there's a lot of candidates that are inside that habitable zone, around their star, that are Earth size, and I think we should start when we now know from looking at our solar system that liquid water can survive outside the habitable zone. You can have these interesting chemistries. But going back to our sample size of one, we know that there's life here on Earth, and we know that these are the conditions where life has thrived. So I think that would be the place to start looking. Even though there might be some really interesting objects out there, let's stick with the habitable zone, Earth-sized planets where there's nothing special about the way Earth formed that we can tell. It's the same processes here as other places. So you're going to have terrestrial planets, rocky planets with, the potential for water on the surface. And I would say that, I don't know, I'd be hard pressed to say specific locations, but that's where I would want to start focusing.
I think we talk a lot about Kepler 452 is a pretty good match, but I wouldn't want a vacation there. Okay, well, thank you so much for joining us for Cosmic Conversations. It's a wonderful and very topical given this week's announcement. I wish we could take credit for having planned that out, but it's just serendipity.
Well, this has been a lot of fun, so thank you.
It is a joy. For all of our viewers, thank you so much for tuning in, both on Facebook and YouTube. We really appreciate it. For our SETI folks, if you want to follow us on Facebook, you can find out about more cool stuff that's coming from our channel. On behalf of myself, Morrison Planetarium, we'd like to thank you, Dr. Bywaters, and our audience for joining us. Without you, this just wouldn't be possible. So from the bottom of our hearts, thank you. For all of our folks at home, please stay home, please stay happy, please stay healthy, and we hope to see you again as soon as our planetarium can reopen. From us to you, thanks, and have a wonderful day.